Welcome everyone to my channel Physics Hub Official. Today we'll learn about J.J. Thomson's atomic model, his cathode ray experiment, the famous Plum Pudding Model, and its main limitations. Let's explore how Thomson's work led to the discovery of the electron and the first idea of atomic structure. Before we begin, let's go back to the early 1900s, when scientists were trying to understand what an atom actually looks like. One of the first successful attempts to describe the structure of the atom was made by J.J. Thomson, an English physicist and chemist. He is also the scientist who discovered the electron, and for that, he was later awarded the Nobel Prize. Let's see how he discovered it, through a very famous experiment called the Cathode Ray Experiment. As the cathode ray first becomes visible as a white beam inside the glass tube. The electrodes appear, with the cathode releasing electrons and the anode attracting them, while the vacuum pump maintains low pressure. The high voltage generator drives the motion of electrons, and the nearby magnet causes their white beam to deflect, showing the behavior of cathode rays. Cathode Ray Experiment, Apparatus. A glass discharge tube with two openings, one connected to a vacuum pump to create a partial vacuum, another connected to a gas inlet. Two metal electrodes inside the tube, cathode negative charge and anode positive charge. A high voltage power supply. A fluorescent screen coated with zinc sulfide. Now we see the mechanism of cathode ray experiment. First, we have a glass discharge tube that acts as a closed chamber for the experiment. Next, a vacuum pump removes most of the air inside, creating a partial vacuum. Two electrodes are fixed inside, the cathode, on the left and the anode, Joe, on the right. The high voltage generator is connected to both electrodes to provide strong electric potential. When the voltage is applied, electrons are emitted from the cathode and start moving towards the anode. These moving electrons form a beam called cathode rays, visible as a faint white or greenish glow inside the tube. The fluorescent screen glows where the rays strike, showing their straight line path. When a magnet or electric field is brought near, the rays deflect towards the positive side, proving they are negatively charged particles. Thomson made some key observations. First, when an electric field was applied, the rays bent towards the positive electrode, showing that they are negatively charged. Second, when lightweight rotor blades were placed in their path, the blades started rotating, proving that these rays are made up of tiny particles having mass and energy. Third, in the absence of an electric field, the rays traveled in a straight line. From these observations, Thomson concluded that these cathode rays are made of negatively charged particles, which he named electrons. By applying both electric and magnetic fields, Thomson calculated the charge-to-mass ratio, A by m, of the electron as A by m is approximately 1.7588 times 10 to the power 11 coulombs per kilogram. Here, the charge of the electron is 1.602 times 10 to the power minus 19 coulombs, and the mass of the electron is 9.109 times 10 to the power minus 31 kilograms. When we divide the charge by the mass, that is, A divided by m, we get 1.602 times 10 to the power minus 19 divided by 9.109 times 10 to the power minus 31, which gives approximately 1.7588 times 10 to the power 11 coulombs per kilogram. This value was first determined by J.J. Thomson in his cathode ray experiment, and it showed how extremely light the electron is compared to its charge. Based on his experiment, Thomson proposed the first model of atomic structure. He said that the atom is a positively charged sphere, and inside it, electrons are embedded like seeds in a watermelon or plums in a pudding. That's why it is called the Plum Pudding Model. According to Thomson, the atom is electrically neutral, because the positive and negative charges balance each other perfectly. Although Thomson's model was an important step forward, it had some limitations. First, it could not explain the stability of the atom. Second, it did not show how the charges are arranged inside the atom. Third, later discoveries, like the nucleus by Rutherford, proved that the model was incomplete. So, Thomson's model gave us the first picture of the atom, showing that electrons exist inside and that atoms are electrically neutral. Even though it was later replaced by Rutherford's model, it laid the foundation for modern atomic theory. If you liked this explanation of Thomson's atomic model, don't forget to like, share, and subscribe for more easy science videos. Thanks for watching.